Hello and welcome to 3D Wonders. In today's video, we'll explore a real-world application of reverse engineering in the automotive manufacturing industry. This time, we'll be working with a steel injection mold using the FreeScan Trak Nova and EXModel reverse engineering software from Shining 3D. Many manufacturers struggle with outdated or missing mold data. Without accurate 3D or 2D documentation, repair and replacement become difficult, costly, and time-consuming. This is where high-precision 3D scanning makes a difference. The FreeScan Trak Nova offers Metrology-Grade accuracy up to 0.02 mm and resolution up to 0.01 mm. It also provides multiple scan modes that adapt to different surface types and detail levels. Now let's see how we transform the scan data into a complete CAD model. We begin by isolating only the necessary areas of the scanned mesh using the Edit Scan feature. This helps keep the workspace clean and focused, especially useful when dealing with large or complex parts like this steel mold core. The first step in modeling is to recreate the basic shape of the core insert. Using 2D sketch tools, I extract curves directly from the scan to define the outer block. This gives us a solid foundation for building the rest of the geometry. Once the curves are extracted, I apply dimensional constraints to define key features more precisely. This helps capture design intent and can be customized based on your project requirements. With the sketch ready, I extrude it into a solid to form the base block of the core insert. A quick comparison analysis ensures that our model aligns well with the original scan. This gives us confidence that we're building on accurate geometry from the start. Next, we begin working on the parting line, a critical feature in mold design. Precision is key here, especially since this line defines how the mold separates. With the help of clean scan data, it's easier to trace and build this feature directly in CAD. I extrude the sketched parting line to create a reference surface. Another comparison check confirms that we're still within tolerance. We continue shaping the remaining sections of the parting line using similar sketch and extrude steps. Each segment is carefully aligned to maintain surface continuity. Here, the analysis shows a small deviation outside our tolerance range, likely due to slight curve misalignment. I go back to the 2D sketch and make adjustments. After editing, the deviation is now well within acceptable limits. To smooth out transitions in the parting line, I begin adding fillets. This helps replicate the original mold more accurately and avoids sharp edges. I trim out overlapping and unnecessary surface areas to clean up the geometry. More fillets are added around critical junctions to ensure smooth flow and a consistent surface finish. Final comparison confirms that the parting line modeling is complete and accurate. Now we move on to the product surface, where accuracy and detail matter even more. This area often contains fine features, so high-resolution scan data is essential. Using the Stacked Section tool, I generate multiple intersection planes that help me trace the complex contours of the product area. I continue sketching directly over the scan, carefully following every line and shape that defines the surface. Once sketched, I extrude the surface and run another comparison analysis. The results show a high level of accuracy. I apply the same approach to another section of the product area, repeating the sketching process to capture all remaining features. Another extrusion, another comparison. Everything's aligning as expected. Now I trim the excess portions of the product surface to clean up the boundaries and prep for merging with other features. A quick deviation check validates the accuracy of the trimmed surface. At this point, I start building the final parting line profile using the same parametric modeling approach. This ensures consistency across all related surfaces. Another comparison shows that the parting line surface matches the scanned mesh precisely. Next, I trim the parting line surfaces using the finished product surface. This step merges the two areas into a seamless transition. I use this unified surface to cut into the original block and define the final core insert shape. A comparison confirms the final core shape is still within tolerance, which means we've maintained accuracy from start to finish. With the main shape complete, I start adding detail, beginning with rib features. These ribs are patterned across the surface. I use the linear pattern tool and estimate spacing based on scan data. For tighter tolerances, you could also measure this directly during sketching. The process is repeated for the remaining ribs, ensuring consistent geometry across all sections. I continue duplicating and adjusting the rib profiles using the same method, streamlining the process while preserving precision. Once done, I cut the solid body using the ribs to define final cavities and support structures. To wrap it up, I model one last rib to complete the entire structure. That concludes the modeling process for this mold core insert. We've gone through every key stage, from scan cleanup to surface generation and detailed features, all while keeping accuracy and efficiency in focus. Throughout this project, we've demonstrated how precise scan data and a streamlined CAD workflow can significantly improve reverse engineering results. If you're ready to bring this level of precision into your workflow, visit 3dwonders.shop to learn more, explore our bundles, or connect with our team. All links are in the description below.